Etheridge, who will talk to us about branching Brownian motion, Brownian nets, and selection in spatially structured populations.
Thank you very much, and thanks to the organisers. It's a great pleasure to be here. Something less of a pleasure to be giving a talk, in spite of my very strongly dropped hints. But fortunately, they did at least take the precaution of inviting Nick Freeman, who's one of the co-authors on this work, so any questions, Nick's somewhere in the audience. And another co-author is Daniel Straulino from Oxford, and Daniel just completed his doctorate. But more generally, this is part of what's become quite a big program of research with Nick Barton, who's an evolutionary geneticist in IST Vienna. And a key player in that has been Amandine Weber, who's sitting there, who'll be speaking later. And I think that this project arose out of a conversation with Amandine. I think I even know which coffee shop we were sitting in at the time. Okay, so usually when I give these talks, I spend a lot of time explaining what's broken about existing biological models and trying to motivate a model that we've introduced. But I'm guessing that as mathematicians, you're not really that interested in that. So what I'm going to do instead is I'm going to take you through a sequence of models of ever-increasing difficulty, though they certainly won't get as complicated as the kind of models you'll see later today, I suspect. And when we get to the model that I really want to work with, I will try to explain why it is the question that we're addressing is of interest biologically, but you can ignore, fall asleep for 10 minutes at that point. And then I'll try to explain how it is that in trying to answer this question, we uncovered what we think is some rather interesting mathematical structure of these models that we introduced for good biological reasons over the last decade or so. Okay, so our starting point, sort of the vanilla model, if you like, is a model of what's called genetic drift. I'm going to try and avoid using jargon, but genetic drift is the name that we give to the randomness just due to reproduction in a finite population. And the Moran model is a very, very simple model of a population which is of constant size, capital N, and all that happens is that at an exponential rate, n choose 2, a pair of individuals is picked from the population, and one of them dies, and the other one reproduces, and equally likely to be either one, okay? And we usually represent this as here's the beginning of time for my Moran model, time moves down, and we represent individuals just by lines, and reproduction events are represented by arrows. So at this reproduction event, the individual at the tail of the arrow produced an offspring which displaced the individual that was sitting at the tip of the arrow. Okay, that's what that picture is meant to represent. And offspring will inherit the type of their parent. Now, we don't observe evolving populations over the timescales of evolution unless we're working in laboratories. What we actually observe is a single realization of an experiment, and from the data that comes from the realization of that experiment, which is us, we try to infer something about the way that individuals and populations are related to one another, and we try to compare that to the predictions of our model. So it's worth recording the predictions of the Moran model. And these are very simple, and they give us a process that we already saw yesterday in David's talk, the Kingman coalescent. So here, what have we done? So this is the same picture as we had on the previous transparency. Arrows represent reproduction events. And time for the Moran model is running down the slide, and time for relatedness, time for my coalescent process, is running up the slide. And at the present time, I take a sample. It's a sample of size 3, and this picture corresponds exactly to that picture. It just got shifted by LaTeX. And as I trace backwards in time, I just follow the lines that code information about the individuals in my sample, and as soon as I arrive at an arrow, this guy is at the tip of the arrow, so I know it was an offspring of the event, and so the ancestral line will merge with that of the individual at the tail of the arrow because they had a common ancestor from that point onwards, and I trace back. With this arrow, we know that this guy experienced a reproduction event, and this was the parent, but this parent was no longer in the sample, so actually the tree is much simpler than is shown in the magenta picture. So one way of seeing what's happening is as we trace backwards in time, these coalescence events are generated by the same, or the reversal, time reversal of the Poisson process that generated our forwards in time events. And so what we see is that each pair of ancestral lineages just coalesces at rate 1, and that's the classical Kingman coalescent. Okay. Now, nobody believes in the Moran model as a model for the evolution of a population. They believe it captures something important. We don't believe any of the models we write down in biology. That's not somehow the point. They're caricatures at best. But what we tend to do is we use a very simple model like the Moran model, and then we take a diffusion approximation which we believe will be robust to the local details of our model. And the classic one that we would take here would be to pass to what we call a Wright-Fisher diffusion. So let's try and explain that. I'm going to suppose for all of this talk that my population consists of two types, little a and capital A. Geneticists call types alleles, so A is for allele. And I'm going to write P for the proportion of type little a individuals in the population. Okay? Well, under my Moran model, because individuals simply inherit the type of their parent, P evolves according to a continuous time Markov chain. And it will change by just 1 over n at most in any given generation. And the way I've chosen to scale my Moran model, I'm already in good shape for simply letting n tend to infinity to pass to the diffusion limit. So you can pull out your Carlin and Taylor and see that in the limit you really will get this stochastic differential equation, the Wright-Fisher diffusion, for the evolution of allele frequencies. What's important is that you would get that same diffusion if you started from any number of other models which capture the same key features as the Moran model, in which everybody is equally fit, there's no spatial structure, the number of offspring an individual has in a single generation has got finite variance. Those are the key features which underlie processes for which the allele frequencies will converge to this diffusion. And equally, in the same way as this diffusion approximates a very large number of local structures, so the Kingman coalescent will approximate a very large number of local structures. And what's nice about starting from the Moran model is that the Kingman coalescent was already describing the genealogy of a sample before I passed to the large population limit, and the evolution of that coalescent didn't depend in any way on the population size. So as n tends to infinity, I'm still going to see a Kingman coalescent for the genealogy of a sample for my population, for the process that encodes relatedness between individuals in my population. Okay. Now, in the title we said selection, so how are we going to add natural selection? So far, individuals have all been equally fit. There are lots of ways of adding selection to the Moran model, and this is almost the one I meant to choose, but as we'll see later, there's a factor of 2 missing. But there you go. So in the Moran model, what we do is that we add what we call potential selective events, or potential events. And at such an event, again, we're going to choose a pair of individuals just uniformly at random from all pairs in the population, and we're going to think about having a neutral reproduction event. But if a little a is chosen to be the individual that reproduces, and a capital A to be the individual that's going to be displaced, we suppress that event. We don't allow it to happen. And in that way, we have a small selective advantage for the capital A individuals in our population. They're always allowed to reproduce, they can displace anything, but the little a individuals are not allowed to displace capital A individuals at these potential events. Okay. And how do I can't remember what happens in my slides next. We'll see. Okay. Oh, there we go. I should be able to remember because the talk was finished at 20 to 10. So, so how's this going to appear in our ancestral lineages and our genealogies? Well, neutral events are going to be exactly as before, and there should be a little bit of purple there, I'm sorry. So this is just the genealogy that we saw before. But now I'm going to represent these potential selective events by dotted lines. And at that potential selective event, as I trace backwards, I don't actually know whether it took place or not. Because to know that, I need to know the type of this individual here and this individual here. All right? So what I do is I add an extra lineage to my genealogy. And to understand the types in my sample, I have to follow this lineage as well as these lineages. Okay? Now, maybe now's a good time to see why. I can't remember again what comes on the next slide. So why did we choose these potential events at rate ns? What's that really going to mean in my genealogy? Remember that for the Kingman coalescent, population size really didn't matter, that we were able to pass to a limit. Well, how often are we going to see these branches? Well, if I'm a single ancestral lineage, this guy, how often am I going to be hit by a potential event? There are n choose 2 pairs, so that's order n squared pairs, and I'm involved in n of them, right? So the probability that at any of these potential selective events I am involved in them is on the order of 1 over n. On the other hand, they're arriving at a rate proportional to n, And so actually, for any lineage in my ancestral sample, such as this one, the rate at which these branching events, these sort of potential selective events are hitting me is on the order of 1. So that tells me that's the right rescaling that we've chosen. It's also right from a biological perspective because selection is rather weak and we actually expect this quantity, we expect this to be the right scaling. Okay, and when we do that, then what happens to our Wright-Fisher diffusion? Well, here we see the slight disadvantage of being a type little a. Essentially, if a little a parent and a a little a parent and a capital A to be killed is what's chosen, this isn't going to happen. So this event isn't counteracted by having a capital A parent and a little a displaced. And as a result, we get a negative drift occurring. And you can see the rate of that drift should be the rate at which I choose little a parent, capital A to be displaced. Okay. Now, this ancestral selection graph doesn't tell me directly what the genealogy of my sample is, but it does tell me something useful, and it's something we're going to want to use. So suppose all I want to know is the probability that everyone down here that I've sampled from my population is type little a. Well, if I call the population at this time P of t, the proportion of little a alleles P of t, and n of 0 the number of lineages that I have sampled, the number of individuals I've sampled, then the probability that they are all type little a is just this expectation, right? On the other hand, as I trace backwards in time, there's no mutation in this model. Everyone inherits the type of their parent, so it must be as I follow these magenta lines, if I want this guy to be type little a, then this guy must also be type little a, right? But when I get to one of these events, well, what happens here? Well, if I want this guy to be type little a, I've got to worry about whether this selective event took place or not. If this incoming line, which is the individual that's trying to displace me, is of type capital A, the reproduction event takes place and I'm displaced, so that's not allowed. So the incoming line must be type little a, but equally, if this guy were type capital A and my incoming line were type little a, then the event would be suppressed. So in order for the offspring of this event to be type little a, both the potential parents here must be type little a. So what that means is that in order for all the individuals in my sample to be type little a, all the individuals at any point backwards in time in this branching and coalescing structure, which is the union of the magenta and green lines, must be type little a. In particular, if I look at the top of the tree, that's what this expression is doing. That's what this duality manifests itself as. So if we put that together, just to make sure we know what's going on, our dual process, which is the number of ancestral lineages that I'm tracing in this now augmented, this ancestral selection graph, which is the true genealogy augmented by things I don't know about, evolves as follows. The number of lines increases by 1 at just a constant rate per line. It decreases by 1 through coalescence, exactly as the Kingman coalescent. And if I want all the individuals in my sample to be of type little a, then all the individuals in the ancestral selection graph at any previous time must also be type little a. Okay, so that's the sort of general picture that we're now going to transfer to a more general setting. Now, the Moran model is obviously a very simple model for genetic drift. Over the last 15 years or so, especially mathematicians, but to a lesser extent also biologists, have extended models of genetic drift to go beyond the Kingman coalescent that we've talked about to a class of coalescents that are known as lambda coalescents. They were introduced independently in 1999 in papers by Donnelly and Kurtz, Pittman and Sagitoff. The term lambda coalescent comes from Pittman's notation. And how do they work? Well, if there are currently n lineages ancestral to my sample, so I'm back in the neutral case now, we're not going to have any branching for a bit, I'll put branching back in later. So for this genetic drift, we only have coalescents, and if there are currently n ancestral lineages, then a transition which involves a subcollection of size j that I've picked, merging, and nobody else merging, happens at a rate given by this integral. So we have j is the size of the collection I want to merge, so I get u to the j, 1 minus u to the n minus j, where n is the total number in my sample, and that's integrated against this finite measure lambda normalized by u squared. Okay. It turns out this is the most general form that these transitions can take for a coalescent which has nice sort of exchangeability properties and for which we will only allow one merger to happen at a time. So I'm not going to allow 2 lineages here and 3 lineages here to merge at exactly the same time. That would be what's called a psi-coalescent. And I guess Jason Schweinsberg is the world's expert on psi-coalescence, and he's somewhere in the audience too. And indeed, there are lots of people in the audience who know much more about lambda coalescence than I do, so we won't dwell on them too long. But it's worth noticing, if you're not used to thinking about them, that Kingman's coalescent comes out as a special case. So let's just check that. So if I take this measure lambda just to be an atom on 0, then what's the rate at which I see 3 or more lineages merging? Well, if j is at least 3, then j minus 2, I'm going to have a u to the j minus 2. J minus 2 is a positive power. I'm integrating it against an atom on 0. I'm going to get 0. So I'll never see mergers of 3 or more lineages. On the other hand, if j is exactly equal to 2, this cancels with that. And when I integrate this against an atom on 0, I get 1. So any pair of lineages coalesces at rate 1. That's Kingman's coalescent, what we were looking at before. All right, so that's backwards in time. Remember, actually, we started with a forwards in time model for our genetic drift. The corresponding forwards in time model is now usually called the Lambda-Fleming-Vio process. It is in the Donnelly-Kurtz 1999 paper. That's a very long and difficult paper, and it can be quite hard to find some of the results. It's also in this extraordinarily beautiful paper of Berthoin and Legal from 2003. And I'm just going to show you a very, very special form of it, because that's what I need for what follows. So again, I'm going to suppose I only have 2 types in my population, little a and capital A, and I'm going to write W of t for the proportion of type little a individuals. And the lambda coalescent that we just saw describes the genealogy of a sample from a population that evolves according to this process, and I'm going to suppose there's no Kingman component. So that just means that that finite measure lambda has no atom on the origin. And then the dynamics of my lambda-Fleming-Vio are just driven by a Poisson point process, which is homogeneous in time. So t is time here. And at each point of the Poisson point process, we specify what I'm going to call an impact, u. And that impact tells me the proportion of my population that will be replaced in a reproduction event. Okay? So what do? Well, when we get to a point of our Poisson point process, we sample a type from the population immediately before the event. And in our setting, that's either going to be a little a or a capital A. I'm going to denote that type by k. And I'm going to replace a proportion u of the population by offspring of that chosen type. So if they're little a, then W of t is going to get this boost. But I'm killing a proportion u of the population, so whatever the proportion of little a individuals immediately before the event, it gets scaled down by a factor 1 minus u. Okay? So after the event, the proportion of little a alleles is given by this expression. Right, so let's just convince ourselves this really fits in with the lambda coalescent. So here's my Poisson point process of events. And we're going to focus on what happens at this event, which happened at time t and corresponded to an impact u. So that means that a proportion u of the population is replaced. I've only got 2 types. Immediately before, which are blue and green. Immediately before the event, I sample an individual uniformly at random from the population. That's this guy. And it turned out that she fell in the blue portion of the population, and that's the parent. So that means all the offspring of the event are going to be that type. And that's this block here. So this height u means these guys are all offspring of the event. These are the individuals that survived the event. They weren't affected by it, but they've been scaled down so that hopefully the ratio of that size to that size is the same as that one to that one. Okay. So how does that tie in with the lambda coalescent? Well, suppose I take a sample from this population, and again, forwards in time I had a Poisson process determining what's going on. Backwards in time, the same Poisson process is going to determine what's happening to my coalescent trees. So when I hit this event backwards in time, let's just take a sample of size 5 and ask, what's the probability that exactly 3 lineages coalesce in that event? Well, I suppose I could brave chalk. We don't have chalk in Oxford anymore. We're a modern university, so I'm not sure if I can still write with it. Which is also why my laptop doesn't work here. I can't connect to the internet here. Okay, so what's the probability exactly these 3 lineages coalesce in the event? Well, it's the probability they're all offspring of the event, right? So these 3 guys being offspring, each of them is sampled uniformly at random from the population, so the probability they're all offspring, is u cubed, right? On the other hand, I don't want these other 2 guys to coalesce, so they've all got to fall in the portion of the population that was not affected by the event, and that happens with probability 1 minus u squared. So what's the overall rate at which I see an event like that? Well, I've just got to integrate over the rate at which I see events of size u, right? And that you will recognize as beta 5, 3 from a couple of transparencies ago. So that's how we, and we don't have chalk because we're not allowed chalk near computers, I remember now. So that's how you make the connection between your lambda coalescent and your lambda Fleming VO. Okay, but what I'm interested in is spatially structured populations. And so what we're going to do is we're going to extend that lambda Fleming VO process to a spatial context. And it's very simple. We're going to have the same sort of dynamic, same sort of evolution, same sort of events, but events won't now affect the whole population all at the same time. They'll only affect the population in particular regions. And I'm taking a very, very special case of this. I'll leave a more general case to Amandine later on. So again, two types. And now W is going to tell me the proportion of type little a individuals at each point x in space. And space for me is just going to be RD. Now my Poisson point process is going to specify not just a time, but also a region that's going to be affected by the event. And for the purposes of this talk, the region's going to be very simple. I'm always going to take it to be a ball of radius r in RD. And those balls are going to appear in a homogeneous fashion, so my Poisson point process is going to have intensity dt times dx. Okay? I'm going to fix the impact u in each event. So here we had a measure where the impact u was different for different events. I'm just going to fix it in each event. It doesn't really make much difference. Okay, and what are the dynamics? Well, at a point in my Poisson point process, I throw down the region which is going to be affected. That's a ball center x, radius r. I sample a location uniformly at random from this ball. That's going to be the location of the parent. And then I sample a type for the parent, from this location. So from the distribution of types immediately before the event at the location z. So if immediately before the event the proportion of type little a was w of t minus c, then the probability that the type I pick is little a is just w of t minus c. Otherwise, my parent is going to be type capital A. And then everywhere in the ball, I do an update. But notice that there are correlations between the updates. So everyone has the frequencies before the event scaled down by a factor 1 minus u. But if this parent is type little a, then everyone in the ball will receive a proportion u of little a offspring. So there are correlations across space here. I don't do this independently at every point. That wouldn't make sense. Okay, so that's forwards in time. So it's a natural generalization, I think, of the lambda Fleming VO model. And then backwards in time, what happens? Well, don't worry too much about it. I love putting up formulae from time to time because I remember once I was a mathematician, I used to be able to do them. And so that formula I believe to be correct. Probably Amandine worked it out. So what happens to a single ancestral lineage? Well, a single ancestral lineage isn't going to move. Nothing's going to happen to it until it's covered by an event. And if an event falls on it, nothing's going to happen to it unless it is an offspring of that event. If it is an offspring of that event, which happens with probability u, then it will jump to the location of the parent of that event. And where is the parent of that event? Well, the parent of that event is at a point uniformly chosen on the region affected. Okay. So the reason this is correct, I encourage you to work it out for yourselves, is that when an event falls, the position of the ancestral lineage is uniform on the event, the position of the parent is uniform on the event, and you're looking at the distance between those. Okay, so a single ancestral lineage will just move around in a series of jumps, and I promise this is the right intensity for that series of jumps, but importantly, in this setting, they're bounded. And lineages can coalesce when they're hit by the same event. So here we have the green are meant to be the ancestral lineages before the event. These three, these are the ones that were covered, ones that lie in this disk. These three were all offspring of the event. They're all deleted and merge into a single lineage, which stems from where the parent was located. Okay? So very simple backwards in time model. What about selection? So now we have a continuous space sort of analog of our Morin model. It's got one or two other details, but it's basically an analog of the Morin model. What about introducing selection to it? Well, there are many, many different ways of doing this. And actually, in contrast to the Morin model, it really matters how you do this. you'll get different genealogies from different forms of selection. But because we're interested in very weak selection, that's not going to be an issue for us. What we're going to do is we're going to suppose that when we choose a parent, instead of choosing everybody with equal probability, we're going to give a slight advantage to these capital A guys again. So again, I've got two types of my population, little a and capital A, and W is the proportion of type little a. And when I have a reproduction event, if the proportion of little a alleles in the region affected is W bar, immediately before the event, then I'm going to assume that the probability of having a little a offspring is a little bit smaller than W bar. It's W bar divided by 1 plus S times 1 minus W bar, and that just means I've given a weight of 1 plus S to everyone of type capital A and a weight of 1 to everyone of type little a, and just done a sample. Right? Now, if selection is very strong, if S is very strong, we will never observe it. A selective sweep will happen so quickly it won't even leave a trace of itself in the population. We'll just have one locus on our genome which everybody carries the same type. And we won't, it doesn't leave us time to actually detect anything at all, and we won't know whether that locus is there because of selection or because of just chance neutral events. We won't have any way of deciding what's happening. So the only form of selection we have any hope of saying anything interesting about is when this parameter S is actually rather small. And in that setting, I can expand this thing as a geometric series. There we go. And I'm going to throw away all the terms of order S squared and higher. And now we begin to get something that looks a bit like our Morin model. And we really benefit from the fact that everything's driven by a Poisson process. Because now, when an event falls, I can declare that with probability 1 minus S, it behaves like a neutral event. And the probability I choose a little a parent is just W bar, which is the same as it was before. But with probability S, it's a selective event. And the probability that my offspring of type little a is W bar squared, which is the probability that if I choose two potential parents, both of them are type little a. Now that's exactly what we did for our ancestral selection graph. Right? So another way of saying that is that I can think of throwing down independent events. I can think of having a Poisson process of neutral events and an independent Poisson process of selective events. And I guess the rates here are actually 1 minus S dt times dx and S dt times dx. So just to emphasize it, a selective event, we sample two potential parents, and only if they're both type little a do we have type little a offspring, and we just choose the parent independently at random from the two that are there, and otherwise it's a capital A parent that reproduces. Okay? So that's giving an advantage to the capital A's in exactly the same way as we did for the Morin model. Now, I did have a movie, but I didn't put it on this computer, and I certainly don't know how to embed it into my files. So this is a snapshot of a very old movie that Jerome Kelleher, who used to be a postdoc of mine in Oxford and now works with Gil McVeigh in statistical genetics in Oxford. So he produced this. So this is exactly the model that we've just described. Out here, this represents little a individuals. So everyone out here is little a. At the beginning of time, we seeded the center of here with a capital A mutant, so somebody who had a selective advantage. And I think the impact, the U, was 0.8. It was quite big in this picture. And what I hope you can see, it's not showing up enormously well, but what I hope you can see is there's a kind of wave front developing. So you can see up here, everybody is type capital A. Down here, everybody's type little a. And in between, we've got this interesting interface. And this is actually where all the interesting things are happening, which is why I can say very little at all about it, because that's where all the interesting patterns of genetic variation are going to be generated. Up here, everyone's behaving as though they were neutral because the people they're competing with are all type capital A, so everybody's equally fit. And down here, everybody's behaving as though they're neutral because everybody's equally fit. The interesting stuff is here. Okay? So we can't say what we'd like to be able to say about that picture. We can't analyze it in much detail. But we can make some progress by thinking about the analog of the ancestral selection graph for these spatial populations. So how does the genealogy look backwards in time, or what does the analog of the ancestral selection graph look like? Well, neutral events are exactly before. Lineages evolve in a series of jumps, and they can coalesce when they're hit by the same event. But now we have to worry about these selective events, and in a selective event, we, again, a number of lineages can coalesce. So this is the region of event, which in a selective event, again, the green are ancestral lineages that are covered by this event. And these guys are all offspring of the event. But now I must follow two potential parents. So it's slightly more complicated than in the Moran model. In the Moran model, we only ever either branched or coalesced in any given event. Here you can see we're getting coalescence of these three and branching into two somehow. So the two things are happening at the same time, but morally this is the ancestral selection graph in a spatial setting. And importantly, we have exactly the same observation as we had for the Moran model, which is that an individual sample from this population is of type little a if and only if all the ancestral lineages sitting in this corresponding spatial ancestral selection graph are of type little a at any previous time. And that allows us to answer questions like how fast a mutant spreads through a population. So if I want to know whether a mutant has reached a point X, I sample an individual at the point X, I allow its ancestral selection graph to go back until the time when I seeded my mutant, when I put it into the population, and I find out whether my ancestral selection graph has lineages sitting in that portion of the population where I seeded my mutant. If it did, then I'm type capital A, and my wave of advance of selective alleles has got at least that far. If it didn't, it hasn't. Okay. Now, what we're going to do is a rescaling. So let me try to explain the biological question we want to ask and why we address it the way we address it. So I already said that you can't observe selection directly because almost any selectively favored allele, the chances that we identify a selectively favored allele at a moment when it hasn't fixed in the population, when it's in the middle of sweeping through the population, are extraordinarily slim. So when we try to detect selection, what we look for is distortions in patterns of neutral genetic variation on the genome. And if we see distortions in those patterns of neutral genetic variation, then we think something weird is going on, and that something weird might be selection. And we compare the patterns to what our models would predict we would see under selection. Ultimately, you have to go and do biochemistry to decide what's really happening. Now, neutral mutation, what the patterns of neutral, how are patterns of neutral variation generated? They're generated by neutral so-called mutations. If there were no mutations, we wouldn't be able to see anything because we'd all look identical by now. And the neutral mutation rate, so the rate at which you see mutations along your genome, is extraordinarily slow. I think it's about 10 to the minus 8 per base pair per generation in humans. It's very, very slow indeed. Consequently, patterns of neutral variation are going to be evident over rather long timescales. And in the context of a spatial population, that also means over rather large spatial scales. So let's think about our neutral population. If I've got to follow it for a time, let's say 1 over mu, until I see a neutral mutation, if I'm following an ancestral lineage till I first see a neutral mutation, how far has it got in that time? Well, it's following a random walk with bounded step size. So it's gone on the order of 1 on square root of mu in space, right? So those patterns of neutral variation, which are happening on a time scale of the order 1 over mu and a space scale on the order of 1 over square root of mu, are probably best observed by looking at a diffusive rescaling. The second advantage of looking at diffusive rescaling is this observation again, that we don't believe in our model. There is no way that any population is evolving according to the spatial Lambda-Fleming-Theo model, but it may be that it captures just enough of the local reproduction mechanism that when we pass to a scaling limit, the predictions we make are the same as if we'd taken a model which was more realistic. Okay, so the idea is that the scaling limit will be robust. So what we're going to do is that we're going to apply a diffusive rescaling to that spatial ancestral selection graph. And the question we're going to ask is, when can we actually expect to observe a signature of natural selection? Or actually put another way, when have we got any hope at all of observing a signature of natural selection? What does that correspond to? It corresponds to saying, well, if I take a sample, when will it look different from a sample from just a neutral population? So when will I have a chance of actually detecting that these branches take place in my ancestral selection graph? And what does that mean? Well, that means that when I've sampled 2 parents instead of 1, well, what's going to happen? Well, it could be that over a very short time scale, they just come and coalesce back together again. And then I won't see that in these diffusive limits. But it could be that they escape to a distance on the order of 1 over the square root of mu from one another. And if they do, then there's some hope that patterns of neutral variation will look different under selection than under neutrality. So the question is, when will we actually see branching when we pass to a rescaling limit of the spatial ancestral selection graph? Okay, I'm going to keep the impact u to be fixed. We're sticking to a simple situation. And for reasons I can't quite remember, I'm going to write n equals 1 over mu, I think, because I find it slightly easier to say n than mu, because I'm now going to talk about 1 over n. So sorry about that. So let's see. It turns out that whether I can detect selection or not is going to be dimension dependent. So let's think about the simplest case first. The simplest case is 3 dimensions and higher. So if I have 2 random walkers who are, so I get 2 individuals born in one of my events. So here's my event. Here are my 2 potential parents. There's some positive probability that the next event that affects either of them is maybe this one, and then maybe this guy's affected by an event. And after a finite number of events, they've moved far enough away from each other that they cannot be overlapped by the same circle of radius r. As a result, they start to behave like independent random walks, and the distance between them is then just a random walk. Now, in 3 dimensions and higher, of course, a random walk with nice bounded variation jumps is transient. And so with positive probability, they actually escape from each other. So they certainly escape to a distance on the order of the square root of n in time n with positive probability. So in fact, all I need in order to be able to hope to detect selection is that on these diffusive timescales, I might see a finite number of an order 1 number of these selective events. Okay? In order for that to happen, remember I'm doing diffusive scaling using this parameter mu, using this mutation rate. That just means that my the rate at which I see selective events has to be on the order of 1 over n, because then in n units of time I've got order 1 events. Okay? So that's saying my selection coefficient has to be on the same order as my mutation coefficient, and as it happens, that's exactly the same as if there were no space. For a panmictic population, it's the same condition to be able to detect selection. Okay? So that's kind of boring in its way, but fortunately no organisms really live in 3 dimensions. In 2 dimensions, things start to get a bit more interesting. So in 2 dimensions, we no longer have this transience of our random walks. On the other hand, they are random walks. We don't yet have Brownian motions. They really are random walkers. If I start 2 random walks in 2 dimensions at distance 1, and I ask what's the probability that they escape the distance square root of n before coming back to distance 1, it's 1 over log n, of the order of 1 over log n. Now, they only have to do that once, and I'm going to be able to observe them. And so the number of branching events that I need before selection is going to be visible is going to be on the order of log n. But if I don't have on the order of log n events, when they come back and coalesce, they've got probability close to 1 of just coalescing immediately. So I need on the order of log n branches in my time interval of length n if I'm going to have a chance of detecting my selection. So that means that my selection coefficient must be on the order of log n over n, because remember, time is getting scaled by n. Now, that is an awful lot bigger than n, than 1 over n. So why is it an awful lot bigger? Well, because I told you that neutral mutation rates genuinely are very, very small. So we're talking 10 times as strong a selection coefficient in order to detect selection in 2 dimensions to in a panmictic population. And what that's reflecting is that if this impact is fixed, what impact really corresponds to is 1 over the local population density. So keeping the impact fixed is saying that the population density isn't exploding locally. It's being controlled. And as a result of that, in 2 dimensions, you have a lot of competition from your close relatives and your near neighbours, right? And in order for selection to take off, it's no good if it's immediately having to compete with its close relatives. If you get killed by your own family, you're never going to take over the population. So what we're seeing in this result is really the interactions caused by living in a spatial environment. And this is actually of great interest biologically, but you have to take my word for that. And, well, what does the ancestral selection graph look like in the limit? If my random walkers do escape to a distance square root of n from each other, which happens with probability 1 over log n, actually they're not going to come back together. They'll stay apart. And on these timescales, what we're going to see is something that looks like a branching Brownian motion, but I put it in inverted commas here because you have to be a little bit careful. it's rather a fine balancing act, because you're producing branches infinitely quickly when you scale time by n, right? Log n per unit time. It's just that most of them disappear immediately. But it means you have to be a bit careful about the topologies you're working in. Okay, but that's not my department, that's the mathematicians I work with. Okay, in one dimension, it's probably the most interesting, or has uncovered an interesting mathematical structure. Biologically, it's still interesting. There are populations that live in one spatial dimension, notably ones that live in intertidal zones or are adapted to particular altitudes. And in that case, the effect is going to be even stronger. So what's the probability that two random walkers started at a distance order 1 apart, escape to root n before they come back together again in one dimension? Well, it's 1 over root n. So now I'm going to have to see of the order of root n of these branches before any of them escape to a distance when I'm actually going to see them. So that means my selection coefficient has to be on the order of 1 over root n, and that's ludicrously strong. That's really very, very strong. So we would not expect, if we had fixed impact, to observe most of the selection most of the selectively advantageous mutants that we're trying to establish in this sort of population. Okay. So that's, as I say, it's kind of interesting biologically, but what I thought you might like to know about is that in this case there's an interesting connection between these spatial Landau-Fleming-Vio processes, or more importantly between their duals, these ancestral selection graphs, and the Brownian net. So let me try and explain how that goes, and I've put if u equals 1, and we'll come back to that in a moment. So let's first look at the neutral case, because it's easier to understand. So let's take u equals 1 and work in the neutral case. So here's time for my coalescing lineages, and here's space. And remember, I'm throwing down events, and that's these magenta bars, all of which are the same size. And the center of the event and the time point of the event is just a homogeneous Poisson process. And now, if I look at what happens to ancestral lineages, they go back until they hit an event, and then because u is 1, with probability 1, they're an offspring of the event, so they jump to a uniformly distributed point, and then I trace back to the next event, and so on. Okay? So what we're going to see is a system of random walkers that coalesce. Now, this is very, very similar to a process called Poisson trees, which was introduced by Landim, Torreson, and someone help me out, Ferrari, maybe, quite a while ago. The difference is that in their setting, instead of choosing a point uniformly to jump to, they jump to the center of an event. And instead of just taking what I'm going to call an exploration path, because this is what Miko in his thesis calls it, instead of taking a path and then jumping when I hit the event, they actually interpolated between the center of the events to get continuous paths. But apart from that, it's the Poisson trees. And what they showed was that if you applied a diffusive rescaling in this example, you would get a Brownian web. So I'm sure you all know what a Brownian web is, but roughly speaking, a Brownian web says that if I start, so now I'm going to start an ancestral lineage from every point in space and time. So up to now I've really been thinking of finite samples, but if I start from every point in space and time, then I can construct this thing called the Brownian web. So basically, if I take any finite deterministic sample of points in R2 and I look at the way that, no, let's start at the one above, because there's a reason it's the one above. If I start from a point in R2, then my Brownian web gives me a path, a single path, which just evolves like a Brownian motion started from that space-time point. Okay, and we're thinking of it as going sort of northwards up the screen. Now, for any finite collection of points, the corresponding paths are distributed as a system of coalescing Brownian motions, so they don't evolve entirely independently of each other. When they meet, they instantly coalesce. Okay? That's what we'd expect from our Poisson trees picture. And the way that the Brownian web is usually characterized is via a kind of self-duality. That's meant to be a W, not an M. Sorry. I don't know how it came out as that. How can I mistype \cal W as M? It's a mystery. So the dual W hat is also a Brownian web, but with time running in the opposite direction. And for any point in R2, if I look at the corresponding path in that dual, it's the almost surely unique path that doesn't cross any path in W. So I have a system of coalescing Brownian motions going with time going in one direction and one going in the other direction, and they interleave each other in such a way they don't intersect. And this property is really first observed by Aratia, and here's a picture that Daniel drew. That should be a solid line. So this is how this works when you're just working on Z2. So this is meant to be a system of coalescing random walkers now going up the screen. So this is the classical setting for the Brownian web, is to think about Z2, not to think about the continuum. So the blue is my web, and you can see from every point on this even lattice, say, I have a random walker, and when two lines coalesce, here's a coalescence point, they follow the same line. And then interleaved, going in the opposite direction, we have the dual web, which is again a system of coalescing random walks, and it has the same distribution. Okay, so that's how you characterize the Brownian web, but that wasn't what we wanted, because we actually have selection in our model. So what happens when we add selection? Well, when we add selection, here's time for my branching and coalescing lineages. I'm afraid I cheated and just edited the old picture. So these events now, these Oxford blue events, are the selective events. And in a selective event, I'm afraid Cambridge blue doesn't show up. There are two parents. There are two parents, and now we must follow both of those parents in order to get our full ancestral selection graph. Okay. Now the difficulty now is that if I try and construct this process started from every point in space and time and apply a diffusive rescaling, asymptotically there's going to be more than one path coming from each space-time point. But what allows one to characterize the limit is that there's a unique leftmost path and a unique rightmost path. So for example, started from here, I follow this line for the leftmost path and this line for the rightmost path. And similarly from here, this would be the rightmost path. And those systems of leftmost paths and rightmost paths form Brownian webs. Well, not quite Brownian webs, because there's going to be a drift, right? But the leftmost path will follow a Brownian motion with a drift, and the rightmost path will follow a Brownian motion with the opposite drift. And it turns out that one can construct an object called the Brownian net, which is due to Sun and Svart, and you can characterize it in terms of these dual webs of leftmost paths and rightmost paths, and their corresponding dual webs. So you have leftmost paths going forwards in time and a dual leftmost web backwards in time, rightmost paths going forwards in time and a dual web of rightmost paths going backwards in time. And the difficult thing about showing that our model, which is essentially captured by this, converges to a Brownian net, the bit that's sort of interesting rather than just technicalities, is to find the appropriate leftmost and the dual leftmost and rightmost paths. So I'm afraid this was converted because my system crashed when I tried to use the original picture, and in conversion it lost the straight line which represented the event, which is here. So this is a selective event. Here's the leftmost point of the interval, here's the rightmost point of the interval. Here's a path coming in, and forwards in time the leftmost path jumps to this parent. So there are two parents here and here. The leftmost path jumps to this parent and then goes on. The rightmost path jumps to this parent and goes on. To get something with the same distribution but in the dual direction, if a path comes in to the west of this westmost parent, it jumps to the extreme endpoint of the interval, the extreme westmost endpoint of the interval. Similarly, here I would go to the right if I'm doing my leftmost web. So here's my, what's this, is rightmost path backwards in time. I jump to the rightmost point and down. If I come in between these two parents, I jump like that. And if I come in on this side, I jump like that. And if you stare at it for long enough, or if you have, I should have drawn it with colors, you can see that this is exactly constructed in such a way that the leftmost, should we do a leftmost or rightmost? Here's a rightmost path going northwards, and here's a rightmost path going southwards, because of course rightmost paths have to stand on their heads, and you'll see they do not intersect. And that's the same interleaving as you see to construct the Brownian net that we saw in the previous transparency on Z2. And that gives us the two dual webs, and that works for rightmost and leftmost. And then there's a certain amount of work, and you pass to a limit, and out comes the net. Okay, but that was if u equals 1. Now, in a paper, I should mention this paper because it's with Nathaniel. So in a joint paper with Nathaniel and Amandine some years ago now, in other words, I can't remember the date, we considered the neutral case with the impact u fixed, but with it fixed not necessarily equal to 1. And we observed, as you'd expect from this thing corresponding to a Brownian web or a Brownian net when you have selection, we observed that if you look at the genealogy of a sample from the population, you just recover a system of coalescing Brownian motions in one dimension. And those Brownian motions coalesce instantly on meeting. And if we change U, all that happens is that we see a change in time. Just changes the clock of our Brownian motions. They still coalesce instantly on meeting. When we put in selection, it seems that one's first guess might be that the same is true with selection, because somehow it's reflecting the fact that when Brownian motions are close together, they really do coalesce very quickly. But when we put in selection, things are really very different. So this is a slightly rough and ready simulation that Daniel has done, and I'm sort of hoping that he'll produce a nicer one before he gets his job in the city. So this is increasing U. And what he's done is he's followed a leftmost path, or he's followed the position of leftmost paths and rightmost paths for different values of U, and he's just looking at the expected position as U changes, right? So if it were a simple time change, as it is in the neutral case, then we just see a straight line like this and a straight line like that. And such lines are embedded in his simulations. But in fact, what we see is that the rightmost particle escapes very much further than if this were a simple time change, and the leftmost particle similarly in the other direction. And this is kind of suggestive that it ought to be possible to work out what this is. Now, very close to U equals 0, this thing's behaving like a branching Brownian motion. And when we get up to U equals 1, it's behaving like, so this is behaving like the extreme particle in a branching Brownian motion, and up here it's behaving like the leftmost path or rightmost path in a Brownian net. But in between, we really don't know how to capture this behavior. So that's an open question for the audience, because I don't think I have a clue how to do it. And I think I'll stop there. Thank you very much.
What topology are you using for convergence to the Brownian web and the Brownian net?
What's what?
What sort of topologies are you using for convergence?
Oh, there's standard ones. You literally lift. Oh, you have to extend things a little bit because we've got catalog paths and stuff. But you just use exactly the technology of sum and spart, and you just lift it up and transfer it over.
So this is something where you see a path emanating from every space-time point or something like that?
Yeah.